Welcome back. In this video I'm going to introduce the ideas of structuring of code in C. In most languages there's a mechanism for modularisation, that is for breaking a large program into smaller ones. In Python, for example, it's the import statement. C doesn't actually have a definition or a mechanism in the language for modularisation. It all has to be done at the system level using separate compilation and cheating things called header files, and that's what I want to cover in this video. So just to remind you, back in Lab 1 we explained that the process of compiling a C program was actually a four-stage process. First of all, the C preprocessor got called. It did things like hash includes and hash defines. These are just text manipulation. The next stage was the C compilation proper, which converts it to the machine language in textual form called assembly language. Then the assembler converted the text version of that into relocatable binary object code, which we'll talk a little bit more about in a minute. And then lastly, the linker, or the link editor, LD, put together the code that you have written together with any library code in order to get an executable module. So I'm going to show you that over here. So first of all, I'm cleaning my directory, and if I list my directory now, I have junk.c, I have something called prog that I should have got rid of, so I just have three source files. The one I'm going to start with is junk.c. Here it is. It's the solution to the quadratic problem from Lab 1. It defines a discriminant function, a print roots function, and a main function. So if I compile that using the -c flag, which we also introduced in Lab 1, and we made use of when we set the build commands for Genie. You may want to look at your build commands and look at the compile command. You'll discover it has a -c in it. So with the -c, we do only the first three steps there. So I'm going to do that now. I'm going to go gcc -c junk.c. If I do that, then I have a new thing created called junk.o. If I ask for information about that by going file junk.o, I get told that it's ELF, executable and linkable format, 64 bits, 64-bit machine, least significant bit architecture, relocatable, can go anywhere in memory. It's the architecture for the x86-64, which is the standard Intel chips we use in our lab machines. The format of the this particular ELF file is version 1, which goes back to Unix System 5, sysv, which is early 80s, so this is pretty ancient, and it's not stripped. Not stripped means it contains extra information in it, which I'm now going to look at, nm junk.o. This tells me the names of the symbols defined in this particular output object file. It contains discriminant, main, and print roots. That's my three functions, and they're of type T, which for weird historical reasons means text, or stands for text, but means code. Don't ask me why. The discriminant is at hexadecimal 0, the main function is at A9, and the print roots function's at hexadecimal 43. But there are some undefined symbols. These are the scanf function, printf, puts, and square root, and a couple of others, which are functions that I've needed in my program. For example, I call square root, and I call printf, puts, and things like that. They're undefined. In order to define them, we need to run that last stage, the link edit stage. So that if I were to go gcc junk.o and specify a -o blah, it doesn't quite work, but what this was meant to do was call the C compiler, give it an object file, and if you give the C compiler an object file, it skips these three stages because there's nothing to do and goes straight to LD. And it was meant to output the file blah, which would have been executable. It didn't quite work because it couldn't find square root, because that's not in one of the default libraries. In order to get it to include that, I have to add -lm, which is telling it to use the library file -lm for math, two-character Linux typist having two fingers only. So when I do that, I get this executable file called blah. There it is, and I can run it. When I run this file blah, it needs three quadratic coefficients, and it tells me the roots are imaginary. How do I use that myself? So far, this is just using it to hook in the my program with the library programs, and I don't generally bother doing it in separate stages. I just use the build button here to do the whole lot in one go. So let's look at an example. Here's a useful program that defines a function for me. It's called my very useful function. It takes an integer argument and returns the integer argument it was given. It's of type int, the function. What happens if I compile that by itself? GCC minus C silly.c. Minus C flag again, stop after compilation. Works fine. If I have a look at my directory, I find that there is a silly.o there, and if I look inside that to find what names it defines, there's just one. It defines my very useful function. No surprise, perhaps. How do I use that? Well, I'll write a program. Here's a program that uses my very useful function. Doesn't define it, just uses it. What happens if I compile that program? Same rules. GCC minus C prog.c. It gives me a warning that there's an implicit declaration. So it's happy to compile it, unless I have the minus W error flag, which I haven't included. It compiles it, but it warns me that, well, I hope you know what you're doing, because I'm just going to guess that's an int function. So we don't like guessing, so we normally require that you put a declaration in. Int my very useful function. In. Now that isn't a definition. It doesn't say what the function does, it merely says what its type is. So with that modification, if I rerun that compile command, parameter names, int my very useful function, what just happened there? I forgot to include the int in argument. I'm sorry, we'll try that again. Now it works fine. So now, if I were to look at my nm of prog.o, I discover it has an undefined very useful function, whereas a minute ago I showed you that the silly.o had a defined my very useful function. So I can put the two together. GCC, silly.o, prog.o. And I'd better call the output something. I'll call it prog. Now I have a file prog. You can see it there. There it is, prog. And I can run prog. And it does this sophisticated piece of C of printing the result of calling my very useful function with the value 10, which hopefully you can work out, prints 10. So far, so good. That's the basic mechanism of separate compilation. I can break my program into smaller pieces. At the moment, it's slightly awkward because my silly thing says what the function does and how it does it. And I had to include that line there to make it work. I had to actually know what the types were. That's annoying. What's much better is to do the following. I'm going to hash include a file that I haven't written yet called silly.h. I'm going to put it in quotes rather than in angle brackets because it's a local file, and I'm going to create myself a new file which is going to contain simply that. I'm going to save that, and I'm going to save it in the right directory or I'll be in trouble, 260 junk, and I'm going to call that silly.h. So that now I can compile the program. It will include that there, so it just copies that piece of code into here, just as it did before, except I had to be explicit about the declaration. I had to know what the declaration was, and if I did any editing of silly.c, I'd have to go and edit the client code here, which I don't want. So I've now got sort of the best modularization mechanism. I've declared the definitions. Sorry, I've specified the definition for the functions. I've defined in this header file what the types are, what the exported symbols are and what their types are. And then I've made use of the type include here, and the linker puts the actual stuff together. So with all those changes, let me rerun that. I'm going to recompile prog.c. I'm going to relink it, and then I'm going to run it. and it all still works. So in my 10 minutes, slightly over, that's the guts on separate compilation. That's how you break a larger program into smaller pieces. In the next video, we'll look at a more sophisticated example from the laboratory. Thanks for watching. Bye.